And hi everyone. So I'm Carolina Mora Lopez. I'm a scientific director at IMEC, leading the team that develops both the probe and the system of Neuropixels here. Just to give you a little bit of an introduction about IMEC. So IMEC is a leading research and development institute for nanotechnology and microtechnology, and it has the headquarters in Leuven, here in Belgium. And together with many industrial and academic partners, we aim at impacting the society with innovative solutions in many fields related to semiconductor technologies, in life science, in imaging, photonics, wireless communication, IoT, among others. So we have a specialized fabrication facilities that allows us to develop specialized technologies that can be combined with the standard CMOS processes, and with also the possibility to do low volume production and manufacturing and advanced testing and verification. And it's because of these capabilities that we are able to develop and manufacture the Neuropixels probes. So this is one of the reasons why this is done here at IMEC. And one of our goals with Neuropixels was to revolutionize the neuroscience research by developing a miniaturized tool that is as powerful as many of the equipments that are still used in many research labs. And of course, some of the main goals of these tools, a part of the miniaturization, was to achieve a very good signal quality, and at the same time allow low power consumption, because we wanted to integrate electronics in this device without causing tissue heating by the operation of these circuits. And those goals are only possible by using a CMOS technology that enable us to integrate these electronics inside the probes. So the probes were designed by using this type of silicon wafer. The specific process is a 130 nanometer CMOS process technology. And we have the facilities at IMEC to develop a CMOS process or a CMOS compatible post-processing fabrication technique to do the electrode fabrication and also the probe singulation. So what is inside the probe are then all the active circuits that allow for the typical signal processing, such as amplification, the filtering, and the analog to digital conversion. So I guess most of you are familiar with the probes, but this is, when you zoom into this probe, what you will see are the array of electrodes that are deposited in the shank with these specialized techniques that we developed here. The probe shank is around 22 micrometers thin. And to be able to fabricate this, we need to use what we call an SOI technology that allows us to have different thicknesses on the same device. So we have the probe base that is much thicker than the shank. And for these electrodes, we develop a very special material, titanium nitride material, that is very porous and that allows us to have also very low impedance, and a biocompatible material that is also very uniform along the shank and very resistant. And one of the main challenges for this fabrication as well have to do with the stress compensation. This is one of the engineering optimizations that we need to do to make sure that the shank is as flat as possible, despite all the stresses that are existing in this CMOS process. So when we compare the designs, we can see that one of the efforts we did with Neuropixels 2 was to miniaturize the circuit while keeping a very similar signal quality. We wanted to miniaturize the circuits to have the same functionality, but in a much smaller device that is also compatible with mice experiments. And all this miniaturization requires also some research on the electrical side on how to develop better circuits that are smaller and that also consume low power, but keeping this signal quality, and all these are not obvious things to do. So part of this more electronic research than is done at IMEC. So until very recent, the portfolio of Neuropixels included the probes that you see here. So we had the very first probe we released was the Neuropixels 1. Then this probe was adapted to develop the Neuropixels NHP that were with a longer shank to target non-human primate applications. And that came in two versions, one with a 25 millimeter shank and one with a 45 millimeter shank. Then we developed also the Neuropixels 2, that is very much very similar probe as the 1.0, but with a much smaller base. And that at the moment we have released the multi-shank, 4 shanks, but we are also releasing very soon the version with 1 shank that will also allow certain labs to do experiments when they only want 1 shank to be implanted. So very recently, we have also released some versions, maybe for the people that attended SFN last week, they may have seen already some posters and some information regarding this. So I will describe some of these products. One is the Neuropixels 2 quad base. So this is basically a new version of the Neuropixels 2 that have 4 times the base, so 4 times more channels as well, while keeping the multi-shank functionality. So the shanks are exactly the same, but you can record from 4 times more channels, in this case 1,536 channels. And the limitation here is that you only have 384 channels per shank. And I saw in one of the in one of the channels in this Slack page, someone was asking about this limitation. So indeed, the limitation of how many channels per shank we can have is because of the limitation of the metal lines that we can accommodate in a shank width. So for this specific technology, the metal wires that we can route in the shank have a minimum width, and we are already using that minimum width, and we have also a number of metals that we can stack, and that will determine the total amount of wires that can be routed. So for the technology we are using, 384 is the maximum. So that's why we come up with that number, because it's a limitation of the shank width for that specific technology. So although here we have the more channels, the limitations is still 384 per shank. We have also released a device that we call Neuropixels 1 HD. So this probe has a very high density electrode array. Here, the electrodes are much smaller, are 5 by 5 microns, with a pitch of 6 micrometer. So this allows to record a smaller cell size, and there is already a printout of a paper. There was also a poster as a event that described the kind of observations that we can do with this probe. So in total, we have 6,144 electrodes in a single shank, with still the limitation of only recording 384 at a time. And the other product that we released is the Neuropixels 1 box. This is part of the data acquisition system. So instead of the big PXI that most labs have at the moment, it's now possible to have a much smaller box that looks like this, where you can connect 2 head stages. So you can support up to 2 1.0 probes or 4 2.0 probes, because you can connect 2 probes to a single head stage. And this will connect to the computer through a USB 3 interface. You also have this breakboard where you can connect input and output signals to other equipment that you want to synchronize together with your recording. So this is basically the very recent releases that can be acquired and be part of your experiments as well in the short term. But I want to also talk about what we are doing in the coming years. So one of the research that we do here at IMEC is how to further miniaturize the probes. So in my team, we are doing research on CMOS design, on trying to develop recording channels, readout channels that can be much smaller in area with the same signal quality and also with low power. We want to use part of this research to be able to develop better devices for the future that we can integrate more channels within the probes. And for that, we are also using different CMOS technologies. Just here for the outlook of what are these ongoing projects. So we have on the one hand, the Neuropixels NXT. So this is an NIH project where we are developing a probe with the same form factor as Neuropixels 2 that will have 1,536 channels. Actually, the number per shank, this is a typo, it will be around 512 electrodes that you can record simultaneously per shank. And we have already published an engineering paper in the VLSI conference this year where we are reporting the performance of this probe. And then in a couple of years, probably this will become like the Neuropixels 3 probe that we will be releasing. And on the other hand, we are also working on Neuropixels Opto. I think there have been some labs testing that. We had a development project where we developed a very first proof of concept of this probe, where we are combining electrical recording with optical stimulation for optogenetics. And now we started a new project where we want to further mature this technology with the goal to make it also one day available as low volume to the community. So yeah, I think this summarizes then, let's say, the outlook of the things that are starting, coming in the short term. Of course, there are many other activities in the much longer term, but they are less well-defined. So probably we will be talking about that in an upcoming workshop as well. Thanks.